Good morning, guys. My name is Subhojit Banerjee. I head the technical division at Abundance AI. Firstly, a note of thanks to the organizers, and thank you guys for coming to this talk. Firstly, a very quick show of hands. Who is using machine learning in production? And who is using Spark in production? Awesome. This is the audience I want to speak to. So I have a bunch of slides and I have a demo. I'll go over the slides a bit quicker so that I can have more time while doing the demo, because this is primarily a technical audience. So in this talk, I'm going to share my war stories. In this talk, I'm going to share my war stories in deploying large-scale machine learning models in production. So big data is not easy. It sits at a confluence of three different, diverse, and very deep fields: machine learning, distributed systems, and domain or business understanding. Now you want to mix and merge these three different fields together to actually make business revenue, which is a very complex task in itself. Gartner found just 15% of companies have machine learning models in production. And the top 5 vendors are all in losses. And 90% of all data lakes fail. So there is something wrong here that we need to address. Obviously, business is not happy with what has been promised and what we are giving back to them. So Gartner did a study to identify why this is happening. The first two reasons are very organizational. Firstly, organizations still have to learn how to take value out of big data. And secondly, the data lies in silos in big companies. It's very difficult to get those data out of those silos. And the third thing is technical expertise in agile model development and deployment is lacking. The intent of this talk is to address the last part, or the third point. How do we democratize large-scale machine learning model development and deployment? And here we have the nailless data scientist actually complaining that Kaggle competition is different from what you can do, what you have to do in production. These are two different worlds. So this diagram that you're seeing here comes from the NIPS 2015 paper, which shows you that only 5% of the code base is machine learning code. If you want to push this machine learning code into production, you have to write this remaining 95% of the code base. You have to write about configuration, data collection, feature extraction, machine resource management, service infrastructure, monitoring, A/B testing. But the media doesn't speak about the other parts of the code. They only speak about this part. And if you see, configuration is possibly a large part of the actual volume of the code, but it's less complex than the machine learning code. So what I'm going to do is take you through this journey of how I pushed a machine learning model into production. I'll first start up with a business use case. I'll explain about the first solution. I'll explain you the problems faced, how I came up with a better solution, and demo this. I'm looking forward to this demo. Hopefully the demo gods are with us today. I'll conclude and I'll take your questions. So this is the TLDR of this talk. After this slide, if you want to leave, you can. But I would really urge you to actually stay back. So the first is, among this TLDR, the TLDR of the key takeaways. If you want the TLDR of these key takeaways, that's the first point. So that is the only point possibly if you want to take away from this presentation, that is it. So a better than random model has revenue generating propensity for business from day one. I'm not talking of all machine learning models. Say, for example, medical grade machine learning models, you want to have more than 0.9 on the RSE curve. But for your standard classification regression problems that you everyday business faces, you can obviously start off adding value add from day one the moment you produce a non-random model. The importance here is to concentrate on an end-to-end strong data pipeline. Peter Norvig sometime back had mentioned that dumb algorithms that can scale beat smart algorithms. But there's a corollary to what he said. And the corollary is you have to invest in a strong data pipeline to take advantage of this data. The second point is PySpark models can be deployed in a scalar pipeline. So there is this war going on between data scientists and data engineers. Data scientists want to code in Python, and data engineers prefer the type safety of the JVM. So I'll show you a way wherein if after you code in your PySpark model with no changes, you can actually deploy that model in a JVM-based pipeline. The third point is Spark models can be scored in near real time. So Spark is a distributed platform, as you know, but because of the distributed tax, it cannot score near real time use cases. But in this demo, I'll show you how that problem can be solved. Spark can be Dockerized. Now, Docker today is the unit of scale. If you Dockerize a component, you automatically get the advantages of CI/CD, A/B tests, the entire configuration management, the dashboarding. So if you can convert your machine learning models or your Spark models to Docker, you obviously automatically can piggyback on the software engineering best practices that has come in. And all this can be done in a matter of minutes. And I'll show you in the demo how this can be done and expose that model in a scalable API. The last point is important for production machine learning. If you are handling personal information, we are in the post-GDPR world in Europe. And if you are, and it's important that we handle personal information very carefully. Anonymized data or anonymized features can give good models and good accuracy. So I'll show you in my test case how I was able to get 0.88 on the ROC curve. So the business use case. Sometime last year, business came up to me and said, "Hey, Subhojit, this is our website, and we want to people come to this website to buy products from this website. Can you find out in real time the intent of the user? That is, whether the user is going to buy or not buy the product, right? It's a trivial problem. However, there are two layers that add non-triviality to this problem. Firstly, the classification has to be real time. And the second thing is it has to be, the features that I use in the machine learning model has to be GDPR compliant. That is mostly anonymized features. But first, to actually create a model, I have to create a pipeline where I get the clickstream data from the website, from the mobile apps, and store it, and to basically create the model, and also to ensure that the model can be scored. I chose a model, open source tool called Snowplow. Previously in this presentation, you have seen people have mentioned about Snowplow. So this is an event collection and enrichment tool. It's completely open source. It is scalar based. Each of these components can be scaled because this is Akka based, and so it can automatically auto scale the incoming load that you get in the traffic. This is the standard Lambda architecture that was used to deploy the same Snowplow model into production. This is a standard Lambda architecture, and this has been done in AWS. But if you want to deploy this in your own data center, you just have to replace the AWS infrastructure components to using Kafka or your own data stores. Okay. So primarily, what it does is it stores the incoming data that comes in is stored into two areas: the real-time component and the batch components. Okay. Production numbers. So we had collected, when we started off this project, we had 23 million events a day. We had 140 gigs of granular data that I collected to actually create the first model. And the cost on AWS was pretty economical because I could get it done in 6 to 12 euros per day. And remember, my intent was to use managed services because finding good DevOps engineer is very difficult. I battle tested, performance tested the pipeline, and as you can see, 99 percentile of the code actually returned in half a second, which was pretty good enough as the first version of the code. So now that we have a end-to-end pipeline that can collect and enrich the data, can we use that data to actually create a pipeline to create a machine learning model? One thing to note again is basically while choosing the model, I have to choose a model that can work on anonymized data. So as a quick and dirty solution, I used Markov chain model. So I took the sequence of web pages visited by the user and created a Markov chain model out of it. I created the model in R, and basically I uploaded to S3 and used AWS Lambda to expose that model out. Right? Happy path. But it's not so happy after all. AWS Lambda only allows you 50 MB of compressed size of your binary. So when I first started off creating the R model, the first hit was 212 MB. So I had to hack on it, get that down to 26 MB, but I would not recommend you work on the, R models and trying to deploy and to shorten the model size on a weekend. It just takes away your entire weekend off. The second point was R is not supported in AWS Lambda. So I created a Python wrapper on top of it, and that worked. But the final nail in the coffin, every time frontend would change, my machine learning model would hit the cold start problem, because the sequence of web pages would completely change, and the model that I created on the old data becomes relevant no more. So obviously, things had to be improved. But were there some learnings? There were obviously a few learnings, because that is what you get after your failures. The effort was worth it to move machine learning, to deploy machine learning or to score machine learning in AWS Lambda, because this was possibly the first time serverless was being used to expose machine learning models in using AWS Lambda. I've been a big fan of John McCarthy, who has been a Turing Award winner. And in 1961, he mentioned that computer science or computers, he was talking about time-sharing systems. So computers, specifically time-sharing systems, would one day mature into utilities. So just like you have tap water, you use the tap water, you just pay for the amount you use, or electricity that you use. Compute, you would only pay for the amount of compute that you use. So serverless, AWS Lambda, you only pay how much, basically for the amount of compute that you use. So this was pretty amazing to actually see firsthand what 40 years or 50 years of development in computer science took the dream to reality. But obviously, there was a need for a better solution. We had to come out of the AWS Lambda R structure to something that was more production ready. But there were a few requirements. The requirements here is I had to decrease the time of models to move from notebook to production. So if I'm using my Jupyter notebook, from there to actual production, I needed to move things very quickly. It has to be super scalable, because this is a clickstream, or a clickstream data actually grows and grows on you. If the project is successful, if the product is successful, the magnitude of data that comes in is very large. So whatever machine learning model you are going to use, or the pipeline that you use, has to be super scalable. The third point is it has to eliminate the recoding of Spark features. So I did not want to code in Python and then again recode the same stuff in Java or Scala, but reuse the effort that I have put in the Python world without very minimal changes in my JVM world as well. And the serving or inference has to be super fast. So this is a real-time use case. I needed to ensure that the models can be scored very rapidly. Going into the technical analysis. For the model serving to be super fast, it had to be out of the Spark context. What does this mean? So Spark is very good for distributed processing, right? But the same distributed processing that is good for large amount of data becomes the bottleneck when you're scoring one row of data. So this means that I have to get the entire machine learning model, the pipeline, the pre-transformers, the post-transformers out of the Spark context, out of the Spark environment to a new environment that can score rapidly on the Spark created models. The second point was it has to be completely vendor neutral. I build the model in AWS and I should be able to score in GCP. I build the model in my local data center. I should be able to score in GCP by moving, and this is the third point, by moving the bundle or the serialized model out of my local data center and then pushing it to AWS, or if I've created the model on AWS, push it to GCP. So the true test of serialization would be, can I zip up my entire machine learning pipeline, email it to my coworker, and can she start coding? Can she start scoring the data immediately? So why is Spark slow in scoring? Spark is very good for distributed processing. However, when you have terabytes of data, the data actually gets stored in multiple nodes. Spark creates this directed acyclic graph, and it stores the lineage and the execution plan. The reason is, if any of your node falls down while in compute, the compute can go back previously to the checkpoint and then start from there, right? But this distributed tax is very good while you have nodes failing for large amounts of data. But when you have one row of data, this becomes a bottleneck for you, because fine, it's one row of data. If the node goes down, I'll rerun it again, but I don't want to pay the extra distributed tax. But in Spark, there is no solution to take a more shortest path for real-time scoring. So I was looking for solutions of how to get the Spark model out of the Spark context. There were a few available options at that point. Some were old, some were new, but I had certain metrics. The metrics does that product support Python and Java and Scala? Is there a possibility of the pre-transformations and post-transformations? Can I serialize the entire pipeline out? Does it support custom transformations? Does it support Spark ML? Does it score for low latencies? Does it have an active community? Does it have a good documentation? Is this free? And does this score multiple data points simultaneously? Pretty stringent requirements, but not all the products could match it. But there was one product that pretty much matched what my requirements were. So finally, these slides are going to be available to you, and I'm not going into each of them. But the final solution that I chose was Mleap. How many of you guys have used Mleap before? So Mleap has been possible due to the good works of Holland Wilkins and Mikhail Semyonik. It's a common serialization format and execution engine for machine learning pipelines. It supports Spark, scikit-learn, and TensorFlow. And once you have this model, once you serialize the model, you can run it in AWS and GCP. For most part, you don't have to modify any internal code. TensorFlow it's a work in progress, and it's completely open source, and it is Scala-based. And you have to, in fact, I had to change a part of the code to make it work on AWS. So roughly, this is how the Mleap look like. Broadly, there are two components, the Mleap bundle and the Mleap runtime. So what happens here is, the rationale here is, if you're using a standard scaler, the math behind a standard scaler is the same whether you are using it in Spark or in scikit-learn or in TensorFlow. So why not have a layer on top of the standard layers to actually create a serialization format, right? And that is where your Mleap bundle comes in. So Mleap bundle is basically a JSON and a protobuf based format that helps you serialize the models that you have created in Spark and expose this out. But once you have created the serialized model out, you need something to actually read and score your data, right? And that is where you have the Mleap runtime. So Mleap runtime understands this Mleap bundle that has been created, and then you can use the Mleap runtime to actually score your models. This is roughly the internals of Mleap. What are the 5 components that you have? the one thing that I want to go to a little bit more is this bundle ML, because this is a very important component. So bundle ML, it provides you the common serialization framework for both Spark and Mleap. It's 100% protobuf and JSON based. So once the model gets serialized out, you can actually go into the pipeline of the zip file, and I'll show you that. And you can actually see how the coefficients, the intercepts have all come out and how that has been mapped to your data frame. So in my notebook, the way I'm going to show you the demo, the top level architecture of this will be, I'll be building a model in my notebook. I'll be using Spark and Hadoop to basically create the model. And Spark is going to use the Mleap architecture. And then once I create the model in Spark, I'm going to use Mleap to serialize the model out. This model that I create is going to be sitting in an Mleap serving infrastructure, and then I'm going to use REST API to basically call this, right? I'm using, only for this demo, I have created a REST endpoint. In production, because it's a real-time use case, you can actually create a jar file, and you can use function calls directly to call your models, which is going to remove latency. Because when you're using HTTP for REST calls, that adds a lot of latency to your code. But the only reason I'm showing you this in HTTP is, or using REST, is because it's much more easier for me to demo. So what are the, currently Mleap actually supports almost all the transformers, estimators, and the models that you have in Spark. Except ALS, the alternating least square, work has been still going on that. And it's very easy to actually do the custom transformations. So you're just one git pull away of creating your own transformers. Now, the demo. This is what I was waiting for. Hopefully, things work out today. So what are you going to see? This is exactly the workflow that I used while deploying the models in production while I was creating. But I can't use production data, or I can't use production code. So I'll use openly available Kaggle data to actually create the model. I'll use a REST-based interface to actually expose the data. Okay. So in production, I actually used a standard. I created a jar file of it and used function calls to get low latency model scoring. So I'll build a model in PySpark or using in Kaggle data in Jupyter Notebook. I'll expose the model in a JSON and a protobuf format. So I'll have the serialized model out. I'll load the serialized pipeline in a Docker container and move this entire Docker container to AWS and to Kubernetes to basically scale the model and expose this out. Okay. One request: if you are not able to see, can you please raise your hand so that I can enlarge the text size? Is this good? Okay. So this is the Kings County Kaggle data set. It's a very simple data set. It's a very small data set. The reason I use this data set is so that I can show you quickly what goes on. So the intent of this notebook is not to go over the data science process, but once you have created the model, how do you deploy this out? So the background here is I'm running this. This is a Apache. This notebook is Python based, and I'm using PySpark. And the background here is Apache Torre that provides a layer between the underlying Spark layer and this notebook. So I'm not going to go over the data science pipeline, but the end goal of this notebook is the data science pipeline is to actually create the features, identify which features actually have the best bang for your time spent. And once you identify the features, I'm going to start the notebook from when I start using the PySpark part of this notebook. Okay. So once I identified the features that are relevant, are the ones which are actually giving good targets, what happens here is after this process, the data scientist is going to throw the model to the data engineer saying that now, Mr. Data Engineer, start coding the entire process in Java or Scala. What happens is when you throw this model across the wall, a lot of assumptions that the data scientist has made actually falls apart. So what you do is you take so the intent here is to just use the same model that has been created in the PySpark world and use it in a JVM or a Java-based pipeline, right? So I'm using the standard PySpark libraries. I'm including the standard vectors, the vector assembler, standard scalars, the entire the usual suspects that we know about. I'm creating a custom schema for the data. This is a house prediction prize, house prediction competition. I'm not going to go into the details, but it has some features on the basis of which you have to create the house prize. Right? I'm loading the CSV file, and if you look at the data frame, this is how it looks like. Okay. I define the continuous and the categorical features. I create the train and the test split. I do the scaling, the standard scaling, and then I one-hot encode the categoricals. I then create the pipeline, and then let me just show you this. So I created the pipeline, and then I create a linear regression model on this. So this is all in the Spark world. We are still in the PySpark world, right? Let me see if the newly model that I've created can transform data or not. Sure, it works. I did check it yesterday, and it's still working. Let me time this and see if what's the latencies that we get. Remember, this is a real-time use case. The data frame that has been created is in my local laptop. To score the model, it's taking 178 milliseconds. Okay, let me do it again. Well, it's now increasing. 190 milliseconds. So this is something that is not acceptable in a real-time use case. So obviously, I need to get this data frame out. So this is where till this point, you would have your data scientists do their work. And now, if this has been thrown to the data engineer, all that you need to do is basically use these two lines, that is including Mleap, and you are serializing this model out. So this entire pipeline that you created, including the pre-transformers, the post-transformers, the actual model, everything gets out and gets serialized in this bundle file that we created. Let me just go over the so this is the one which has been created now. And so if you look at the So if you see here, we used a linear regression model, and inside the bundle file, you have all the components that were part of the pipeline. Let us go into one of these components and see what it has. Each of this component has two files, the model.json file and the node.json file. I just copy pasted that into another text editor because it was not possible to enlarge. I'll show you that part as well. So the model.json file has the coefficients, the intercepts, the array indexes for your one-hot encoder, the decision trees for your random forests, and the node.json file wires your model to your data frame, right? So it tells you these are my input columns, these are my output columns, right? So fine, we created this PySpark lr.zip, the linear regression model. We have serialized it out. But then I need to expose that and actually score data. So I created a Docker file. Let me just show you a Docker file that actually has so this is just for a test. In production you would actually have more layers to the Docker file. And what I did was basically after creating the serialized model, I used the Mleap serving as a Docker component, and then I started the Mleap server that is going to listen on a particular port. Okay. I'll just show you the command. So what I'm doing is I'm running the API server, that is the Mleap API server, and it's going to run on port 65327, and the volume of that Docker container is mapped to the same Docker to the directory where I have copied the PySpark model. So now it's listening on that port. The next step is basically can the newly created lr.zip file that I created, the serialized model, I need to push that to the API server. So this, let me show you the. So this was the model, the PySpark lr.zip. I had moved it to a /models directory, and now I push that model to that API server that is listening for requests. Okay. Now the moment of truth. Can we score the model on this or not? And how long does it actually take? But very quickly, let me also show you the file that I'm going to send. This is the JSON file that has the schema and this one row of data that needs to be scored. So these are the features of the site, of the property. And basically, using these features, I want to know what the actual price of that property is. The actual model is not so much important as much as it's a working model, and basically how do we expose that model out. Okay. So the model is the API server is listening on 65327, right? And I'm going to send this JSON file that you have to this API server. So voila, we have results, but we still have 197 milliseconds. That's not good enough, right? I told you that, well, we would be getting in less than 50 milliseconds. So what went wrong? The thing here is once you get, so Mleap is smart enough to know that once it loads a model, but it doesn't load it completely until it gets the first request. When you run it the second time, now you can actually see the values. So the model is not being cached. You can immediately deploy the model, new model, and you will be again getting the sub 50-second millisecond latencies. But only for the first request, it just primes it up. Okay. So this is the code that is running on my laptop, right? But this doesn't end. We remember the 95% and the 5% part of the code that we were talking about. We still have to use the code, the 95%, to move it into production. And the good way to do that is if we can already piggyback on something that has been already done. So sometime back, Amazon came up with something called as the Amazon SageMaker. So Amazon SageMaker allows you to create your models. And in this case, I did not use Amazon SageMaker to create the model, but the Dockerized container that you just now I showed you on the laptop, I used that Docker container to push that Docker container into the ECS registry of Amazon, and then basically create an endpoint to expose the model. The good thing is you can immediately see that with a click of buttons, I can create the weights. So I can actually create a endpoint where if I want a canary test or an A/B test, I can create, if I know that there's going to be a huge load, I can actually change the instance type to M2 media to M2 large or more beefier machines. And I can also do an auto scaling. So I created this endpoint. And then let me see if this actually can score the Docker container that we just now created. So I'm using Postman to actually post this message. This part of the code is the JSON file that you've seen, okay? And this part is basically the endpoint that I showed on SageMaker. Cool. And I get 684 milliseconds, which is pretty high, right? But you have to remember that the SageMaker, the EC2 machines that are running, this is running an island data center. And network traffic has huge latencies. In production, what's going to happen is these models are going to sit in the same Docker container and hopefully in the same AZ itself. And so thereby, you're going to totally eliminate the latencies or the network latencies that are associated with it. I did one more thing as well. I took the Kubernetes engine. I created a Kubernetes cluster, and the same Docker container that I showed you, I also uploaded it to the Kubernetes engine and exposed it as an endpoint. So I'm going to send the same data to Kubernetes endpoint that I just now created. And so this is where it works. It's much more faster than what we saw in SageMaker, and that is because, can anyone take a guess? I use a EU data center. So that's the demo part. I'll go back to the presentation because I have 2 minutes. In production, remember the use case that I was talking about? I got a result of 0.88 on the ROC curve, and I was able to get in 50 milliseconds, in less than 50 milliseconds. And that was built on a single random forest model. The importance of a single model is very important because it helps you scale. It is very important for model explainability. And I did that on 100 gigs on data. And the most important part was it was done on completely anonymized features. So how was this possible? This was possible because of this Recsys 15 paper. You can go back and look at the paper. This has all the features. There is not one-to-one mapping, but it looks very similar in production how I was able to use those anonymous features and get a good result out of it. So I wanted to just check if the results that I got was by fluke or was there some signal behind the feature engineering that I did. So I participated in the Kaggle competition just to use the available data and use that single model just to check how it's performing on publicly available data. And even there, you can actually see that the accuracy was 0.89. So the model accuracy that I got in production was not a fluke, and it seems there is a signal to the feature engineering that has been suggested in that paper. Okay, conclusion. Conclusion here is computer science started from 1837, right? And this is possibly a diagram of man's attempt to control electronic chaos. These were two parallel paths that were going on, right? But during this, in order to control chaos, there were many things that came in. Version control, CI/CD, Docker, and all this that you see here did not happen overnight. There was a lot of pain, a lot of calls in the midnight to actually solve problems, right? And this is how the best practices have evolved in the computer science world. Now, there is data science. Pardon me, but your data science models are not snowflakes. They are still as simple as web applications are, in the sense that they take in inputs and they give outputs. So why not containerize them and basically use the same currency that the computer science has fine-tuned for a long time to structure and deploy applications in the cloud, right? Or basically scale your applications. So the end here is, please Dockerize your machine learning models, and you can actually piggyback on the possibly 100 years of work that has been already gone in computer science. I want to end this talk with a small anecdote. This comes from the book Art and Fear. The ceramics teacher came to the class and divided the class into two halves. Half A, she said, is going to be solely evaluated on quantity. That is, how many ceramics pieces are you going to produce. The other half, she said, is going to be evaluated on the quality. That is, how good are the aesthetics of these pieces. At the end of the day, a very unique thing came out. The highest quality of the pieces came out from the group that was being graded for quantity and not quality. This is very unique. How did this happen? It turned out that while the group that was being evaluated for quantity were rapidly producing new and new pieces, they were learning from their mistakes and producing better pieces. However, the group that was being evaluated for quality were sitting there ideating and philosophizing without actually producing any results. So how does this relate to our machine learning world? Models are similar to these ceramic pieces. Data changes, the shape of your data change, the external environments change, new regulations come in. If you realize that models have their expiry date, a start date and an expiry date, by which they have to push out of a model of the data pipeline, and newer models have to come in, then, and we iterate this process, we are going to solve this complex problem of pushing machine learning models to production. So that's been my presentation. These are the references, and please shoot your questions.